Okay, so today it will be the final discussion on solidification, and this will be the last of the material on the midterm. On Friday we will start diffusion. So briefly on Monday, this slide deck should be up on Carmen. I uploaded it. Did it not get published? Okay. So we talked about Scheil solidification, right? And we know that we have a directional freezing effect. So the solid, because of local equilibrium, is lower in solute than the liquid, right? So we reject solute, and the liquid becomes more and more concentrated until eventually we hit the eutectic composition when the material spontaneously freezes into alpha and beta, right? The eutectic is defined as liquid freezing directly to alpha plus beta. And so we need to consider what happens when these two phases solidify. So the eutectic is a composite structure of alpha plus beta, typically a lamellar type structure. But what we have most of the time, if we're thinking about actual engineering materials, we're typically in this pro-eutectic solidification regime, so that what we have is regions of pure alpha and the eutectic, right? Now, it's important to remember that the composition of this pro-eutectic particles, these are not constant, right? The composition is going to vary from the center where the nuclei started out to the edge, right? So the composition at the center of the particles is going to be given by K times your partition coefficient times your initial alloy composition. And then you'll have a gradient structure, gradient in composition out until you hit the eutectic region, right? And the eutectic typically is going to form this either a lamellar structure like this, or a rod-like structure like this. So from in your books, this theta, this is the magnification. For the image, this is, again, a really bad way of doing micrographs because I put this in the presentation, right, which is at a different scale than what it's printed in the book, so the magnification's different, and then you're looking at these either printed out or on your screen, so it's at a different magnification. So that's why we always should put proper micron bars in our images rather than a magnification value. This is a TEM image, so this is at a much finer length scale than the lamellar structure, right? And obviously the volume fraction of the beta phase in the rods is smaller. Right. Okay, so in the eutectic, we have alpha and beta growing simultaneously. So we have to have mass transport in the liquid in front of our growing solidification front. So B, element B, or component B, is going to be rejected from alpha, and A is going to be rejected from beta. So we have to have B diffusing this way and A diffusing this way. And the rate at which these two phases can grow is going to be dependent on the rate of how fast this diffusion can happen in the liquid, right? So if the way to make this the fastest is to make alpha and beta as thin as possible, right? then you have a shorter diffusion distance and you can have the faster growth. But of course, that means we have to pay the energy penalty for creating this alpha beta interface, right? And remember, alpha and beta have a high enthalpy of mixing, right? Otherwise, they would be completely miscible, right? A and B would be completely miscible. So because there's a high enthalpy of mixing, you can imagine that this interfacial energy is not going to be cheap, right? There's going to be a fairly significant cost. So the balance here then is going to be that this interlamellar distance is going to be dependent on not only the diffusivities, but also on this interfacial energy. So Nathan's got a question. So if solidification happens first on the outside, yeah, so we'll talk about that when we get to ingot solidification. All right. Okay. So there's a lot of sort of analysis in the reading in the book about this. I really, for the purposes of this class, I really just want you to understand sort of conceptually what goes into this. If you want to get into it in more detail, take the physical metallurgy class next year. I'm pretty sure that Professor Fraser will talk about this in greater detail. If we, most of the time, we're in what we call these off-eutectic alloys, meaning that we're hypo-eutectic, so we have less solute than the eutectic point, right? In which case, we now have all the complications of alloy solidification, plus the added complication of eutectic growth. So we have dendrites that grow, right? Provided we're in a regime here, we have our compositional supercooling, right? If this liquidus line has sufficient curvature to it here, and our partition coefficient is less than 1, or I'm sorry, we don't even need the curvature, that just enhances it. But if our partition coefficient is less than 1, we're in a regime where unless we have really steep thermal gradients, we're going to have compositional supercooling, and we're going to have dendrites that grow, and the solute is going to be, the excess B is going to be rejected into the liquid, leaving to a very common microstructure in cast metals, which is a dendritic structure with a eutectic interdendritic. All right. And so this is what a lot of castings end up looking like, right? The dendrites themselves exhibit what we call coring, right? So we have composition gradients from the center out, right? And so remember, this is going to get richer in B as we go out. If this is alpha, this is primarily A, we're going to get richer in B as we go out until we get to the eutectic, right? So I'm giving you guys a heads up. It's quite likely that you'll see a question on the exam where you have to think critically about these concentration gradients, right? Okay, so I want to talk just a little bit about two important processing steps, or two important processing manufacturing processes. First is ingot solidification, right? So virtually all the metals we use are melt processed and alloyed in the liquid state, and then they are cast either through a continuous casting process, or an ingot casting process. Most or cast directly into a final shape, right? So they could be cast and forged into a final shape, but those examples are very much like what happens in an ingot. Continuous casting is very much like what happens in weld solidification, right? So by talking about ingot solidification and fusion welding, I want to give you a flavor of what's happening in sort of both of the primary ways of dealing with solidification in metals, right? And it also helps that, you know, half the class is welding, so I should at least pay some lip service, pay some a little bit of attention to welding as a manufacturing process and a materials processing route. I forgot to close my email, so it's going crazy. So I apologize for all the binging you're hearing. Okay, so if we cast into a mold, so this is the cross section of a tall rectangular prism, which is a common shape for casting. Generally, our ingot is going to have three regions. We've got this region of fine grains, and my phone is going off in the background. So we have three distinct regions. We've got this region of fine grain, which is what's called the chill zone around the outside of the mold, right? And this is where we have fast heterogeneous nucleation along the mold wall, right? And because nucleation is easy, we get lots of small grains. It's probably a survey wanting to know who I'm going to vote for. And then we get this columnar growth region. And then in the middle, we get a equiaxed zone, right? And these sort of lines here, these are not really highly schematic, right? This is actually what an ingot cross-section actually looks like. And in this columnar region, these grains can be exceptionally long, right? So does anyone have a sense of why we would get columnar growth here? Any guesses? And why we get an abrupt transition to equiaxed grains? Energy cost is always a safe guess, but in this case, it's not.
As it cools, it goes into a different phase region?
No, you get this even if it's a single phase. Well, okay. The equiaxed region is dendrite arms breaking off and nucleating new grains. I have to be careful about what I say about this columnar region, because you do need, if this was a pure metal, it would be different than a sort of an engineering alloy, right? You would need you wouldn't get as pronounced of a columnar structure unless you had thermal dendrites. Right. So, but anyway, let's take a look at each of these layers, right? So in the chill zone, we have easy homogeneous nucleation, right? And let's just assume for the moment that these nuclei are random with respect to their orientations, right? So you can have, you know, a nuclei that's crystal orientation with respect is this way, or this way, or this way, or this way, right? So these nuclei happen at any direction. We know that the dendrites have easy growth directions, right? What's the typical growth direction for cubic metals?
1, 0, 0.
The 1, 0, 0 directions, right? So the dendrites will grow along the 1, 0, 0 directions that is most closely aligned with the thermal gradient, right? So dendrites that have the 1, 0, 0 direction parallel with the heat flux direction will grow straight out. The nuclei that are tilted a little will essentially grow, and they will grow and intersect with the dendrites that are growing straight out, right? So these ones that are tilted will be stopped, right? First off, they'll have less driving force because they're not growing quite as parallel, right? The heat flow direction, right? So they won't grow quite as fast. The ones that are well aligned with the heat flux direction will grow a little bit faster, and these ones will then intersect and stop, right? So essentially the chill zone is regions of small grains that each correspond to a different nucleus, right? And only the favorably oriented ones will grow out into the bulk of the ingot, right? And that's the origin of this columnar zone, right? So we have our off-angled nuclei grow, they impinge, and they die. The parallel ones will continue to grow. They'll grow secondary arms, and a new primary dendrite arm can form off those secondary arms, right? So this then becomes one columnar grain, okay? So single crystal, I talked about nickel superalloys, right? And how single crystal turbine blades are incredibly important for air transit. The structure of that, as you might imagine, is, if I was on campus, I would have an actual blade to hold up and show you. But let's pretend my coffee cup is a turbine blade, right? My 100 direction is along the length of the blade, right? And it's a single crystal with many interconnected primary dendrite arms that grow up in this direction, right? So a really important solidification mechanism, and that's how they make these single crystals, is they actually grow them through a twisty passage, so that you so that you're selecting for a particular orientation. Only certain crystals can survive, right? So they're not, it's a step above directionally solidified, because the directionally solidified grains are still, they're columnar, but it's still a polycrystal, right? So the pigtail for casting was actually developed, right? But was actually developed by a group of different people. And so no, you don't actually need a seed crystal for superalloys. For things like single crystal growth of silicon, for silicon wafers, a Kolsky growth mechanism, then you do need a seed, right? Yeah, the pigtail forces all the near parallel columns to impinge, and you end up with just one single crystal. Only the one that's growing perfectly parallel to the direction grow, right? So this is what's happening in the columnar zone, right? This interdendritic region here, this is called the mushy zone. So the region where we haven't fully solidified, right? But you've got solidifying dendrites growing in. The length of this mushy zone depends on both the temperature gradient and the non-equilibrium freezing range of a particular alloy. Right? So the question I have, though, is what is the orientation of these grains, of these columnar grains? Right? I have different columnar grains, right? My heat flux is going this way. How are these grains related relative to each other? But first, you sort of notice in the picture, you see that the grains that are growing more or less along the heat flux direction survive, and those that are at a little bit of an angle run into each other. So the turbine blades, Ethan, are grown as single crystals, right? In terms of ingot casting, these grains can be really huge, right? These can be, many centimeters long, right? So typically, if you have a casting like this, you would then need to do a large forging or some other processing, rolling, reduction, right? Typically, you don't use a cast microstructure in this state, right? So we'll talk about thermomechanical processing at the end of the semester. But we have these orientations, right? The question about single crystals versus very low angle grain boundaries, that's a matter of, I guess I would say, semantics, right? When do you call it a grain boundary, right? Is 1 or 2 degrees, does that make for a grain boundary, or is that just a bending of the crystal lattice, right? So I don't know. Okay, so what about the orientation of these, right? So we know that they're growing. So let's pretend the heat flux is this way. We know they're growing with the 100, right? But essentially we have freedom of rotation about the 100 axis, right? So essentially in the columnar grain zone, we have the grains that are mostly separated by a rotation about this 100. So the lattices tend to be located like this. Yeah, I've got a bunch of cubes. I'm not like a super fast cuber, but I enjoy it. It's like my meditative thing when I'm on Zoom meetings, is just to sit here and do a couple quick solves when I'm at risk of falling asleep. Right, so these are all all these orientations are all related by simple twist around the 100 directions for the most part. Okay. So then we go into the Equiaxed region, and how does that form? Well, the Equiaxed zone really consists of these grains randomly oriented throughout the center of the ingot. These grains tend to nucleate from broken off or melted off dendrite arms in the mushy zone. And this is due to convection currents, right? And the convection currents in the center of an ingot can actually be fairly violent. I mean, it's not like white water rafting kind of violent, but enough motion to stir up and break off these dendrite arms. Okay. When we're dealing with ingot solidification, we really have to consider shrinkage effects, right? So most materials are going to shrink on solidification, right? Water ice being one of the rare exception, right? If we have a narrow freezing range, right? So if we have a partition coefficient that's close to 1, right? We have a small distance between our solidus and liquidus lines. The mushy zone is also very narrow, right? As this outer shell thickens, the solid is less dense, so the level of the remaining liquid in our mold or our ingot continuously decreases, right? And that leads to a central deep cavity or pipe down the center of the ingot, right? So generally the way you get around that is you have a hot top on top, right? So you have extra material that's above your ingot that's considered waste that's going to be cut off. So all of your waste is up there, and you don't have a deep central cavity down the center of your well. If we have a wide freezing range, the mushy zone can occupy essentially most of the ingot, right? What in that case, we don't end it with a central pipe. What happens is the interdendritic channels close up, and as the last liquid solidifies, we end up with pores or voids internally, right? So these types of defects are one of the reasons why castings are rolled or forged, right? Is we want to close up these defects, right? Anytime you have a liquid processing of metallic metals, right? Whether it's a casting or a weld solidification, you're going to have defects, right? There's no way around it, right? A huge part of designing a weld joint and designing weld filler metals and weld processes is managing those defects, right? Is getting your process window in a range where they can be minimized. But anytime you have liquid metal processing, you have defects. And that also means additive manufacturing, right? Laser, powder bed fusion, and 3D printing of metal structures. The whole thing is full of defects. It's full of voids. It's full of, right? It's a huge mess. So they have to go through a process of hipping or hot isostatic pressing to try and close up a lot of these pores or voids, right? So there's lots of different ways to do it. None of them get rid of everything completely, right? In large ingots, we also have regions of macro segregation. So we talked about coring, which is microsegregation on the scale of the dendrite arm spacings. Macro segregation happens on the scale of ingots or castings, right? And this is due to, we have shrinkage due to solidification, right? So as we solidify, we have solute rejected to the liquid, right? And then the liquid moves around, right? So up here, these are big pores, right? These are like the cavity or central pipe, right? So essentially these are designed, this ingot is designed to be chopped off here. This is also a bottom fill ingot to stop entrained gases and things like that from coming in, right? So most of the time with large ingots, they will be bottom fill. But for macro segregation, we have the shrinkage, we have density differences in the interdendritic liquid, density differences between the solid and liquid. So we have gravitation, right? And then we have temperature-induced convection currents. So we have mass flow over very large distances, right? And these can be on the length of meters, right? For really big, castings, right? Microsegregation can be fixed by a homogenizing heat treatment, right? We can diffuse our solute to be uniform. Macro segregation, this needs to be fixed by deformation processing, forging and rolling and recrystallization, at most of the time at high temperatures, so we have easy diffusion, right? And we also have to have good casting and solidification process design, okay? So this is a really simplistic overview of ingot casting and solidification. I want you really just to get the flavor of it. Professor Lau teaches an entire class on liquid metal processing, and there's a lot of really good resources in the MSE Foundry Club, right? So if you're interested in this, right, there's a lot more that you can explore, right? For welding, I apologize to the welders because I'm going to be a little bit over simplistic, right? You'll get a lot more details of this from Professor Fink in WeldNet 1. Does she teach WeldNet 2 as well? Or does Professor Ramirez teach WeldNet 2?
I think it's Lau.
What's that?
I think it's Lau.
Oh, okay. But anyway, for those of you who are not welders, right, we have to consider what the temperature profile around a weld looks like, right? So we've got a spot, right, that's going to be at the center of our weld, and the weld is going to traverse this way. So up here, we have unmelted metal. Back here, we've got solidified metal. We've got a weld pool that, depending on the heat conduction in the metal, is going to be more or less ellipsoidal on the surface, or more spherical, right, as our diffusivity and heat flux or heat transfer go up, right? And so the region of the melt pool is actually really complicated, right? So we've got a melt pool that's traversing, right? We've got a thermal gradient from the top to the bottom. So we've got very large convection currents. Depending on the process, we may actually have other things like pressure from our illuminating radiation that leads to like Morangoni, I can never remember the name of it, begins with an M. Convection, as well as other different types of convection that are happening, right? So, but keep in mind, we generally have an ellipsoidal. Yes, thank you, Nate. Marangoni. Right, we generally have an ellipsoidal thermal gradient that's moving in this direction, okay? The composition of welds, right, we can either have an autogenous weld where we don't have a filler metal or the filler metal is the exact same composition. Most of the time we're using a different filler metal, and the choice of that filler metal is really important, and why we do certain things becomes really complicated. But it's important to know that generally the weld filler metal dilutes the melt. Okay, so if we look in microalloyed steels, the weld melt pool might contain only 50% or 70% of really important alloying elements like niobium and titanium and vanadium, right, as the base metal, right? The base metal, especially if you're welding thick plate, is also a really effective heat sink, right? We also effectively have zero barrier to nucleation, right? Because we're melting metal and then we're solidifying on it, right? So we already have solid present, right? We already have nucleated big chunks of stuff there. So there is no nucleation barrier. We already have solid of the same composition ready there. Since there's no barrier to nucleation, we have little to no undercooling, right? If we're thinking about our common arc processes, right? TIG or MIG or stick type welding processes, the arc temperature is exceptionally high and the base metal is cold. So that means we have really huge thermal gradients in our liquid, right? And what does that mean if we have no very high thermal gradients, right? We don't have to worry about compositional supercooling, right? So we don't get the same type of dendritic structures that we get in a ingot solidification, right? Of course, this is process dependent, right? So some processes have lower temperature gradients, right? But for the most part, if we just think about arc welding, we don't have any real compositional supercooling that we need to consider about, okay? So we have the same type of columnar growth here, except now we don't have long dendrites here, right? We have more of a planar growth front, right? So we don't have a distinct sort of mushy zone out front here. But we do have a thermal gradient that changes with time, right? So at the first layer, we have a heat source here. Our grains are always going to grow in the direction of parallel to the heat flux direction, right? But then as our heat source moves, our growth direction changes, right? So what we end up with is this layer of columnar grains, right? Where we keep growing until essentially the heat source is far enough away, then we'll nucleate a new layer that will grow towards where the heat source is, right? So if these are temperature isotherms, we're always growing perpendicular to the isotherms, right? So the orientation of these crystals, right, will also tend to have a twist type relationship because 100 is still the easiest growth direction, right? But back here, this interface, right, tends to have a smaller grain boundary with a twist component like this. Right? So you can imagine now the effect of the weld speed is going to affect the weld microstructure, right? So if you're a good welder and have a consistent bead, then you get nice solidification structures that look like this. If you're a bad welder like me, you get a huge mess. But let's just pretend we have good welds, right? So the growth direction is always in, so this picture, we were looking from the bottom of the melt pool up, right? So this is the top layer. This is the bottom of the melt pool into the base metal. Here we're looking at it from the top down. This is the cross section of the weld. This is our melt pool, right? We still are always growing in the direction of the heat flux, right? So perpendicular to the temperature isotherms, right? So if we have a low velocity and a high moving velocity, we have different shapes of the melt pools, we have different isotherms, so we end up with a different type of grain structure, right? If we move slower, we might have multiple layers of grains, whereas if we move faster, we'll generally have two columns of grains that meet right at the center line of the weld. Right? So it's important to remember when thinking about the solidification structure of welds is that we're always growing, we're always going to follow the steepest temperature gradient. All right? So if we think about what's happening, right? The temperature gradient close to the edge of the weld looks very different than on the weld center line, right? So
there'd be more deformation towards the edges then?
So not necessarily, I guess it all depends on what you mean by deformation, right? So if we think about let's think about the center line, right? So if we're near the center line, the heat flux direction is always this way, right? Along the center line of the weld, right? And that means, and the velocity is this way, right? So essentially we just have a simple cosine rule, right? Like in physics 1, if we project our growth, our 100 type growth direction along the heat flux direction, right? These well-oriented crystals can grow, right? And will tend to grow this way. If we think about one at the edge, the 100 crystal direction is going to still be aligned more or less along the direction of the highest thermal gradient. But now the highest thermal gradient points not in the direction that the weld pool is moving, but it points more towards the center line of the weld at first, right? And then it bends, right? Then as the melt pool moves on, now this direction changes, right? Whereas if we're a grain on the center line of the weld, it's still pointing towards the melt pool. So the direction of greatest heat flux doesn't rotate, on the center line of the weld while it's constantly rotating on the edge of the weld, right? And so that means that crystals out here are going to have to bend to keep up, or we're going to have to nucleate crystals at a new orientation, right? And that's why for these slow-moving welds, we see these crystals that seem to follow in these curved arcs pointing towards the center line. Yeah, it's not exactly parallel. It's the cosine rule. The velocity is going to be dependent on the cosine of the angle between the 100 direction and your heat flux direction, right? But I want people just to think about this more conceptually than quantitatively for right now, right? Whereas the high velocity, right, the solidification happens much faster and things just grow out, right? They don't have a chance to bend. But these crystals near the edge need to change their growth orientation as they go. Okay, so important notification, that's the end of material for the first exam, right? So powder, like for additive manufacturing, or powder for powder? Okay, for AM. It's basically still the same, right? You can think of an AM built part as being nothing but weld, right? It gets a little more complicated because you have remelting between layers, right? Like you did with if you have a multiple pass weld process. But essentially, powder AM for metals is nothing but weld. Your whole structure is weldment. Okay. No, the test is the 21st, I think, right? Was what I said? Yeah, the 21st. I just want to make sure everyone has some time to review and ask questions and get all the homework in, and all the homework solutions will be posted this week, so that you'll have that to study to help you with your studying. Okay, so Friday we will get started on diffusion, right? And this is kind of like what's going on. So diffusion will go fairly quickly, right? Right, this phase here for solidification took a lot of time because there was a lot of really sort of fundamental theory. But we'll notice that now you'll see this diffusional phase transformations goes much more quickly because the same things apply. We still have nucleation, we still have R star, we still have everything that we have in solidification, except that our rates are going to be dependent on how fast and how easy things can diffuse, right? But other than that, we've learned about 70% of what we need to be able to discuss solid state phase transformations, right? So even though this is really important for both metals and ceramics, we've already covered it. And the same thing for vitrification and crystallization in glasses and polymers. We've covered a lot of what we need to know about this. So these topics go by, 2 and 3 will go by pretty quickly. Even though they take up a large amount of sort of reading in the book and things like that, right? And then Martin-Sittig transformations, we're going to be talking about in a little bit more of a qualitative sense, simply because to really do martensitic transformations justice, there's a huge amount of crystallography in there. And a lot of, at this stage in your career, you don't necessarily have that background, right? So martensite and martensitic transformations, which govern the behavior of things like shape memory alloys, are really important in things like thermal barrier coating, ceramic thermal barrier coatings, right? The most common of that is YSZ, or yttria stabilized zirconia. The yttria is there to prevent the martensitic transformation from cubic to tetragonal in zirconia, right? So that's the only reason why the yttria is there, is to prevent this transformation from happening. And if that transformation happens, it means the coating spalls off your turbine blade, and then your turbine blade burns up. Not good for the life of a jet engine to have the blades burn up on you. So martensitic transformation is really important for steel, but also really important for a lot of other materials as well. Okay, so take care. We'll see you Friday, and have a good one.